Welcome you all in my next lecture. So in my last lecture I talked about or in fact I discussed the concept of mixed derivative theorem, like mixed derivatives like partial derivatives of second order. I already introduced the notion of partial derivative, directional derivative and total derivative for functions from Rn to Rm, and then in my last lecture I talked about mixed derivative theorem. That means if the mixed order partial derivative exists when they are equal. And then I talked about mean value theorem. Okay, I already discussed mean value theorem in this setting, and now my plan is to talk about Hessian. Okay, I will introduce what do I mean by Hessian, and then Taylor's theorem for functions of two variables, and of course as an application you will see linear approximations and increment estimation. So my major aim is to talk about Hessian, what is the concept of Hessian, how it comes. So my plan is to talk about that in these lectures. Okay, so if you remember that in my last lecture I talked about that when mixed partial derivatives equal. Okay, I should say that in the beginning I said that I already talked about mean value theorem, but which is not the case. In fact, I didn't discuss anything about mean value theorem. In fact, I think later on in my next lecture I will talk about mean value theorem. So there was a typo for that, yes. So okay, so this part I have discussed when mixed partial derivatives are equal, right? So first of all, if mixed partial derivative exist, then there is a question, or we have seen some examples that in some cases they equal, in some cases they do not. But then I want that, okay, is there any condition we can put on the say mixed partial derivative, so that then I can talk about, yes, if they exist then they become equal. Then you just recall that these two theorems are there. If I have a functions f from some open subset Rn to R and take x naught is a point in S, then suppose dij and dji, that means this is called mixed partial derivatives or second order derivatives. If that two exist, that means dij, dji, if this mixed derivative exists in a neighborhood of the point x naught. So that means I am not only talking about the existence at the point x naught, rather I am going to talk about the existence of mixed partial derivatives in a neighborhood of x naught. So that I want some another condition. So what is that? Not only mixed partial derivative exists in a neighborhood of x naught, at the same time I demand that this should be continuous at the point x naught. Now continuous, if I want to talk about the continuity of some function f at some point, that means I need to have the function should be defined in a neighborhood of x naught. So the theorem says that if I have a function f from a subset of Rn to R, and suppose dij and dji both mixed partial derivative exist in a neighborhood of x naught, along with the fact that both of them are continuous, then I can say that yes, these two mixed partial derivatives are always equal. So that is the one theorem. And there is a lighter version, that means I do not need that many assumptions or that strong assumption to talk about the equality of mixed partial derivatives. You can relax a little bit. What do I mean with that? Okay, so this is, there is a typo, remember last class I said, if I have a functions f from S, an open subset of R2 to R, again I am just restricting in n is equal to 2, consider the point x naught in S, and suppose you see in my last theorem what it says that second order mixed derivatives should exist. That means of course first order should derivative exist, that means dif and djf, that means dif and djf, that means partial derivative of f with respect to xj variable and with respect to xi variable, that should exist. Then only I can talk about the partial derivative of f with respect to xi xj and xj xi, right? So that means this is automatically there. So first partial derivatives of f with respect to xi and xj variable exist, then I can think about it as a functions from again some set S subset of Rn to R, and then I can talk about the partial derivative with respect to again xj variable and xi variable. So that means if, so that means dijf and djif exist, it automatically implies that dif and djf exist, and both the mixed partial derivative exist in a neighborhood and the continuity. Now look at this theorem. I am assume that fx fy exist. Of course first order partial derivative of f with respect to x variable and y variable should exist, along with I want only one mixed derivative should exist, that means f suffix xy. That means first you take the derivative with respect to x and then with respect to y. So that means only one mixed derivative exists in a neighborhood of the point x naught, along with that mixed derivative should be continuous. So that means the difference between the hypothesis of this earlier theorem is that I want the existence of one mixed partial derivatives, of course first order partial derivative with respect to x and y variable exist, along with I want only one mixed partial derivative should exist in a neighborhood of x naught along with the continuity. Then also I can conclude that yes, both the mixed partial derivative exist. That means if one of the existence of mixed partial derivatives implies the existence of other mixed derivatives, and not only that, their value should be equal. So this is kind of assumption is little less compared to the earlier theorem. But if you remember, if you somehow think about that, okay, so what I am starting with the functions f from set A subset of R into R, and then I demand that when mixed partial derivatives should equal. So first I assume that yes, if the mixed partial derivatives they exist in a neighborhood of that point x naught, and if the mixed partial derivatives they are continuous, then I say that yes, they are equal at that point x naught. Now the question is, suppose you have a functions f, and suppose your mixed partial derivative exists but they are not continuous, then what can I say? If they are continuous, of course the value becomes same that we just seen in these two theorems. But suppose mixed partial derivative exists but they are not continuous. Now I am going to talk about two examples where you will see, even if suppose my mixed partial derivative exists but they are not continuous, then in some cases they are equal, in some cases they are not equal. Yes. So this is one of the example. So this kind of examples you already seen in my last lecture. So this is a functions in fact from R2 to R. Okay, I already calculated the mixed partial derivatives at the point 0, 0. So this is the breaking point. So f of xy, which is nothing but the quotients of two polynomials if xy is non-zero, and if it is 0 if xy is 0, 0. So that's the given function is there. So now I already discussed many times that if I have this kind of functions, then you can easily calculate the partial derivative of f with respect to x variable and y variable very easily, because if the point xy is non-zero, then you just think about this as a function, so you can easily do that. So only at the breaking point, that means the point 0, 0 origin, it is the breaking point, there you have to check the or you have to calculate the partial derivative explicitly by using the definitions. But if the point xy is non-zero, then it is perfectly alright, it is a quotient of two polynomials, you can easily calculate partial derivative of f with respect to x and with respect to y. Just suppose I want to calculate partial derivative of f with respect to x, what you have to do? You think about y is constant, think about the functions of x variable and just perform the derivative. So therefore, if xy is non-zero, then you can easily calculate this part, this is fine. So only part you have to calculate by definitions is that at the point 0, 0, this is the breaking point. But if you remember in my last lecture, so this is if I go back, yes, so look, so this is the functions I already discussed in my last lecture, and you see, look, calculated. So first observation is that mixed partial derivative exists at every point, R2. However, are not continuous or continuous except at the point 0, 0. That means you can see that mixed partial derivatives these exist at every point in R2, okay, but these mixed partial derivatives are not continuous at the point 0, 0. So since it is not continuous at the point 0, 0, then I do not know whether the value of the mixed partial derivatives at the point 0, 0 equal or not. In this example, even you can calculate the mixed partial derivative at the point 0, 0. I have calculated here. So look, this is the one. So fxy 0, 0, which is the value is exactly equal to -1. Mixed partial derivative fyx at 0, 0, which is exactly equal to 1, but they are not equal. So in this example, so that means it says that, okay, look, so this is the one. So that means the mixed partial derivatives, that means f suffix xy or del to f del x del y at xy exist for all xy in R2, okay. So if xy is non-zero, that portion you can easily calculate, and just only part is that 0, 0, you have to use the definition, though I already calculated in my last lecture. So this is the value is -1. Similarly, you can calculate the mixed partial derivative, that means del to f del y del x. So there also you can, this part you can easily calculate if xy is non-zero, just by keeping one of the variable fixed and you just perform the derivative like the real valued functions of real variable, you can do that. And at the point 0, 0, I already calculated this is exactly equal to 1. So that means what I observed is that if xy at the point 0, 0, which is not equal to fyx at the point 0, 0. However, mixed partial derivative fx f suffix yx that exists at each point in R2. So therefore, I can talk about the continuity at the point 0, 0. Now look at the kind of expression of f of x, f suffix xy and f suffix yx. You see this is not continuous. I have written here f of xy and f of yx are not continuous at 0, 0. Why? So continuity means what? So I have to show that limit hk goes to 0, 0 origin f x y, okay, at hk should exactly equal to f of x y at the point 0 0, right. So, that means the limit should exist as hk approaches to 0 0 of the function f x y, and if it exists, it should be exactly equal to the value of the function at the point 0 0. That means that is the definition of continuity I know. So, if this is the case, then I will say that yes, my mixed partial derivative f suffix x y is continuous at the point 0 0. Now, look, forget about this right hand side. Now, look this limit. This limit actually does not exist, because look at the functions. Your function is f x y, which is nothing but quotients of this. If x y is non-zero, I have this expression, and it is exactly equal to -1 if x y is 0 0. Now, look, so limit does not exist means what? So, that means I am approaching to the origin. I already shared this kind of argument earlier. So, this is my origin. If the limit exists, suppose the limit of the functions exists at the point 0 0, that means whatever directions I can approach to 0 0, the value of the limit should be exist and their value should be equal, then only I can say that yes, the limit exists. But if I say that okay, the limit does not exist, that means the negative way. If I talk about that the limit does not exist, then what you do, you approaches to the origin in two different directions and say that okay, in one direction I have the limit is giving one value, and another direction you are giving another value. In that case, I can easily say that limit does not exist, because if limit exists, whatever directions I approaches to that point, in particular here is origin, the value should be equal. So, this is very kind of by just looking at the expression of the functions f x y, you can easily see. Look, the numerator what? Numerator is highest degree is 6, right? So, each of the coefficients has degree 6. Now, look at the denominator. This is also x square, then to the power q. So, this is also 6. So, in that way you can guess. So, that means if I take the path y is equal to mx, so in that case it will give something. That is how one can guess. Just look at the numerator, look at the denominator, see the power. If they somehow power is same, numerator power is same and denominator power same, means I am talking about the expression, that is polynomial in xy in each saman, that means the expression x to the power 6 is a highest power is 6. This is x4 y square, that means 4 plus 2 is 6. So, that means in numerator you have a highest power of the polynomial in xy is 6 and denominator also 6. That means you can at least try, okay, let us take the part y is equal to mx, then what will happen. So, now if I take the y is equal to mx path, that means if I approaches to the origin via any straight line with some gradient m, if this is my straight line, though it is not exactly a straight line, yes. So, this is with gradient m, suppose this is my y is equal to mx, then how, let us see, you just put the value. So, that means if I approach, so that means I want limit or xy goes to 0, maybe you can write it as xy goes to 0 0 with the path y is equal to mx of f x y at the point x y. Then what will happen? See, you have the expression, right? So, this expression, so you put the value. So, that means this should be limit x y approaches to 0 0, y is equal to mx path, and then just put the value. So, what will happen? If I put y is equal to mx, then you see x to the power 6 will come out. So, that means if I have x to the 6, will some function of m will remain. So, that means first one should be I think 1, this should be I think 9, y is equal to mx, right. So, that means it should be 9m square, okay, minus 9 m4, okay, minus y is equal to mx, that means m to the power 6 divided by y is equal to mx. So, that means it should be x to the power 6 will come out, you will have y is equal to mx, right. So, that means it should be 1 plus m square divided by 3 to the power 3. So, what will be the limit? So, the limit will be exactly the value of the limit is, if I write it here, it should be actually 1 plus 9 m square minus 9 m4 minus m to the power 6 divided by 1 plus m square to the power q. This differs for different values of m. So, that means the limit will be different for different values of m. So, therefore, I am approaching to the origin in different path, however, the limit will be different. So, therefore, limit of f x y as x y approaches to 0 0 does not exist. So, therefore, forget about the continuity, it will not be continuous. And the same way you can talk about the continuity of f suffix y x, that means mixed partial derivative of f with respect to y variable first and then x y, that means f suffix y x, that is also not continuous. So, that means in that case my mixed partial derivative exists, but they are not continuous at the point, and at the same time they are not equal. So, let us see one example where mixed partial derivative exists, they are not continuous, but the value becomes equal. Let us see. Yes, this is one of the example. So, this again it is a functions form, it is a functions from R to R, right. What my functions, if xy is non-zero, it should be x square y square divided by x square plus y square, and 0 if x or y is equal to 0. Again, as I said, so you can easily calculate the partial derivative, first order partial derivative, that means del f del x and del f del y. You can easily calculate. Of course, if xy is non-zero, as I already said, what you look at the definition of the functions, only breaking point is 0 0. So, that means you have to just calculate at the point 0 0 using the definitions, and if xy is non-zero, if the other vector xy is non-zero vector, then it is a very nice function. It is again a quotient of polynomials. So, what you have to do, if I suppose want to perform the or calculate the partial derivative of f with respect to x, what I will do, I will just keep y as a constant, think about as a functions of x, and just perform the derivative. And similarly, calculate the partial derivative of f with respect to y, keep x is constant, think about as a functions of y variable, and perform the derivative. So, that part is perfectly all right. So, only at the point breaking point 0 0, there you have to use the definition. That also you can easily calculate it here. Okay. For example, if I calculate, just I am telling you that how things works here. So, simply, so for example, del f del x. Okay. So, at the point xy, say xy is non-zero. So, this should be equal to you just perform the derivative. Suppose if xy is non-zero, then what will happen? Just if xy is non-zero and I want to calculate the partial derivative of f with respect to x variable, think about y as a constant, think about this object, keeping y is constant, think about is a function of x, and perform the derivative. Use the Leibniz rule, that is it. So, what you have to do? So, this should be like 2xy square times 1 by x square plus y square. Okay. So, this is 1 plus x square y square, and then you have to take the derivative of 1 by x square plus y square with respect to x variable. That means minus 1 by x square plus y square whole square, and then it should be 2x. Correct? You can calculate it, not an issue. You can easily calculate it. What is this? This is x square plus y square whole square. This should be 2x y square times x square plus y square minus 2x cube y square. And do some algebra, I think 1 2x cube y square will get cancelled. So, you will end up with, I think, 2x. So, this term 2x cube y square get cancelled. So, that means 2x y4 divided by x square plus y square whole square. So, this is the partial derivative of f with respect to x variable at the point xy if xy is non-zero. So, only part is remaining to calculate the partial derivative of f with respect to x variable at the point 0 0, because it is the breaking point. There you have to use the definitions. So, therefore, I can say that del f del x at the point 0 0. Now, what is the definition? Just calculate it, limit h approaches to 0, f of h comma 0 minus f 0 0 divided by h, right. So, that is what you have to calculate, right. So, at the point 0 0 I am talking about. What is this? This is limit h approaches 0, f of h 0. Now, given function f is given, right. Now, f of h, x is h, vector x is small x is h, and y is 0. What will be the value of the function? This will be 0. f 0 0 is given to be 0. So, this is 0, that means 0. So, the partial derivative of f with respect to x variable at the point 0 is 0. So, therefore, if I write it clearly, so therefore, I have del f del x at the point xy, which is exactly equal to 2x y4 divided by x square plus y square whole square. This is true if my vector xy is non-zero, and this is 0 if my vector xy is 0 0. You can calculate it, right. Similarly, in the same calculations, you can also calculate the partial derivative of f with respect to y variable. Again, if the point xy is non-zero, if I want to calculate the partial derivative of f with respect to y variable, then you just think about x is constant, think about it as a function of y, just perform the derivative, you will get it, and at the point 0 0 you just use the basic or kind of primary definitions of the partial. Again, you will calculate, I think partial derivative, you just calculate it, I am not calculating again the same way. So, del f del y at the point 0 0, it again will be 0, and at the point xy what will happen? It kind of this kind of things, I am not doing it here. So, therefore, now I have the existence of first order partial derivative of f at xy running over whole R2. right? So now let's see the second order partial derivative. Now again this is a function, very nice functions. It will be of quotients of polynomials if xy is non-zero 0. If 0 and xy is 0, again it will be a breakpoint at the point 0 0. So that means if I want to perform the partial derivative of these functions, that means just you have to calculate the partial derivative at the point 0 0, at the point 0 0 using the definitions, and if xy is non-zero, you just use the usual way, like think about x is constant and perform the derivative, or y is constant, perform the derivative. So that means let's see, if just I want to calculate that what is called f xy at the point 0 0. At the point 0 0, let me see what. So because if xy is non-zero, you can easily calculate by performing the derivative with respect to y variable keeping x is constant. Then what will happen? So just use the definition, limit h approaches to 0, fx is 0 minus fx 0 0 divided by h, right? That's the definitions of f suffix x comma y, x times y at 0 0. That means you perform the first partial derivative of f with respect to x variable and then y variable. Oh sorry, I think this is a mistake. So this should not be the case. So this is not the case. So this should be actually limit k approaches to 0, because already partial derivative of f with respect to x is done. Now I am talking about the partial derivative of fx with respect to y variable. So that means this is limit k approaches to 0, f of x 0 comma k minus f of x 0 0 divided by k. And what is this? Limit k approaches to 0. fx, you know, I have already calculated fx at each point xy. So at the point 0 k, what will be the value? Look, 0 k means x is 0, so that means it will be like give you this one, but x is 0, so that means this will be actually 0. And what is fx 0 0? This is actually given 0, so 0 by k, so that means limit is 0. So that means you can calculate the mixed partial derivatives f suffix xy at the point 0, so of course I have written this is actually 0. Similarly, you can do the mixed partial derivative f yx at the point 0 0. There also you will get the, in the same way you can do that. There also you will get the value will be 0. However, so that means I have just written explicitly here actually. So I think both mixed partial derivatives, you will have this kind of expression, you have to perform. See, only fx part I have done. Similarly, you have to calculate fy, and then again you have to calculate f suffix xy and f suffix yx. So only at the breakpoint you have to use the definition, and if xy is non-zero, then you can just keep one variable fixed, think about the function as a single variable and perform the derivative. Here you will see in that examples, they are equal. You see, I have written they are equal at the point 0 0, because value of the functions fxy and fyx at the point 0 0, it's 0 0. Okay, it's 0 actually. However, these are also not a continuous function like in the earlier argument. Look, again, look at the quotients. Okay, so again, numerator you will have highest degree 6, x to the power 6, then x 4 y square, 4 plus 2 is 6, x square y 4. Again, if I want to talk about the continuity of f suffix xy and f suffix yx at the point origin, again just same argument, you come to the origin in two directions. So take the path y is equal to mx, and that you can guess why, because its numerator and denominator have the similar kind of degrees. So numerator has 6, denominator also 6, so that means you can easily guess, okay, if I take the path y is equal to mx and approaches to the origin, let's see. Same way you can conclude that if I approaches to the origin with the path y is equal to mx, it will give the different values of, that means I should say that limit does not exist. So that means limit x y approaches to 0 0, f of x y at 0 0, this limit does not exist. Just now I have explained in my last slides. That means you just come to the origin through the path y is equal to mx, so you will get a function of m, and that function varies for different values of m. And therefore, you can conclude that the limit of fxy or fyx at the point 0 0 does not exist, and therefore the function is not continuous. So this example says that, look, I have examples where mixed partial derivative exists at the point, at every point, but the functions or mixed partial derivative is not continuous. However, the value of the mixed partial derivative at the point 0 0 are equal. Okay. So therefore, so theorem says that, that means this is a kind of sufficient condition. So not only I need the existence of mixed partial derivatives, but also I want them to be continuous at that point to talk about the equality of mixed partial derivatives at that point. So these two examples says like that. So that means this is sufficient, continuity is needed. If I do not have the continuity, in some cases it is true, some cases it is not. Okay, so one exercise I have given to you. So again, this is a kind of functions if xy is equal to xy divided by x square plus y square to the power whole square if xy is non-zero. Again, it's a map from where to where? It's a map from R2 to R, right? So I want that, okay, examine the existence fx fy. Then I keep on telling you that to talk about the partial derivatives of f with respect to x variable and with respect to y variable, you just at the break point, at the point 0, 0, you just use the principal definitions of the partial derivatives. And if xy is non-zero, so it is a very nice, again it's a quotient of polynomials, so you can perform the derivative keeping one variable fixed. So again, you can calculate easily fx fy at each point x naught y naught. So you will see this will exist. Similarly, you can calculate all the second order partial derivatives. That means these are mixed partial derivatives fxy fyx, and again this is del 2f del x square. That means you perform the partial derivative of f with respect to x variable first, again you perform the partial derivative with respect to x variable of the functions del f del x. Similarly, this fyy. So these are all second order partial derivatives. You can calculate, again it should exist at each point. Check whether this fxx plus fyy is 0, whether it is whole. Once you get the expression, then you can easily calculate that fxx at the point xy plus fyy at the point xy, whether this is 0 or not, or if it is 0, which are the points. And finally, you can talk about, well, I just said check that whether my function is continuous at the point 0, 0 or not. Well, the guess is that you can check that this function is actually not continuous. So one of the way to check is that, okay, sometimes it is useful by changing your Cartesian coordinate to the polar coordinate. Actually, that is important sometimes. Here what I will do, just if I just give some hints to the last one, that whether I can talk about the continuity of f at the point 0, 0. So what you do, take x is equal to r cosine theta and y is equal to r sine theta, right? So that means you change into polar coordinates. So that means what sort of functions it will be? It will kind of, this function will change it to, like if I say f to del of r theta, what is this? So xy, so that means this should be r square sine theta cosine theta and divided by what will happen? X square plus y square, right? So that means you just use the trigonometric rule. What will end up with that? It is r to the power 4. If say xy is non-zero, that means r or theta is non-zero. Okay, and what is this? This is same as 1 r get cancelled. So that means this should be sine theta times cosine theta divided by r square if r theta is non-zero. Okay, and of course r theta is 0, 0, that value is 0. So this is 0 if r theta is 0, 0. So change it to the polar coordinates and then talk about the continuity. Then you will see that this limit does not exist actually. So that means if r approaches to 0, so what will happen? So this is, by look at the functions, see if r theta is non-zero, so that means it is sine theta cosine theta divided by r square, right? So if I want to talk about the continuity of f at the point 0, 0, that means somehow I have to talk about whether the limit xy goes to 0, 0, okay, xy goes to 0, 0 of fxy. That means I want to talk about limit xy goes to 0, 0 f of xy, whether that limit exists or not. If it exists, whether it is equal to the value of f at the point 0, 0, right? Now to change it to the polar coordinate, this is same as in a Cartesian coordinate xy goes to 0, 0. If I convert it to the polar coordinates, that means I need the r, that means the kind of distance from the point xy and origin, or distance of xy from the origin. This is the r, right? So that means this simply limit r approaches to 0 of the function f to del r theta. So this kind of conversion will be there, but look at the function. This is nothing but limit r approaches to 0 sine theta divided times cosine theta divided by r square. Now numerator sine theta and cosine theta, so this is actually bounded quantity, right? It is bounded by some constant, but what will happen in the denominator is r, and if r approaches to 0, it blows up. So therefore limit does not exist, and therefore the function is not continuous. That is one of the way to talk about. So to change it to the polar coordinate. However, you just use the, again, epsilon delta definitions, or you can take in two paths. I think, yeah, I think even if you take two paths like y is equal to 0, and if I approaches to the origin through y is equal to 0, then what will be the limit? So limit xy approaches to 0, 0, okay. If I come, so this y is equal to 0, that means I am approaching to the origin in this direction. Y is equal to 0 means I am approaching, sorry, I am approaching in this direction. in x-axis. So what will happen? So because y is 0, so that means this is the definition of the function. So that means this limit. So that means this is xy divided by x square plus y square whole square. Since y is 0, so therefore this will be 0. Okay, that's first one. And if I come up with y is equal to say x, then what will happen? So y is equal to x. If I say consider the limit xy goes to 0, 0, 0, 0, say y is equal to x. Will it give something? Let's see. So y is equal to x means x square, yes. So that means this should be y is equal to x, right? So that means xy divided by x square plus y square to the power whole square. What is this? This is limit xy goes to 0, 0, okay, and y is equal to x. So then y is equal to x, what will happen? This is x square divided by y is equal to x. So that means 2x square. That means this should be 4 times x to the power 4. Okay, so that means what will happen? So this is same as limit xy goes to 0, 0, y is equal to x path, and what will happen? This will be 1 by 4 x square, and this is infinity. So that means I can come to the origin first via x axis, it will give the value 0, and if I come to the origin along the y is equal to x, it blows up infinity. So therefore limit does not exist, and I can say that since limit does not exist, so forget about the continuity of f at that point. So therefore function is not continuous. However, so these are the exercises you should do, like calculate the partial derivative of f with respect to x variable, y variable explicitly, and as I said, how you have to do that, just look at the breaking point. You have to calculate the partial derivative at the break point just using the definitions, principal definitions, and if the non-zero point, if the function is nice, it depends on what sort of functions you are given. If the function is very nice, you keep the one variable fixed and just perform the derivative with respect to other variable. Okay. Okay, I think I should stop here. Okay, so what I have done today, actually very little I have done. So I have just said that, okay, when mixed partial derivative, if the mixed partial derivative exist of a given functions when they are equal, okay, 2 theorem I have discussed. Okay, and along with that I say that yes, if you look at the statement of the theorem, I need the continuity of the mixed partial derivatives. Then 2 examples I have discussed where you see that even if my mixed partial derivative exist, but if they are not continuous, then I cannot conclude that the mixed partial derivatives at that point they are equal. So in some cases equal, in some cases they are not equal. In my next class, I will talk about that one more concept, that means when I will say that if I have a function f from say set or some open set S of Rn to R, when I will say that that function belongs to C1, that is a notion called C1 or C2. So that means sometimes C1 stands for the one's continuously differentiable functions. Okay, so if I have a functions from R to R, so C1 means function should be differentiable, number 1, and derivative should be continuous. Now if I have a functions from R to R, then derivative is also a functions from R to R. So that means if my function is differentiable, so and the derivative is a functions from R to R, and if the derivative is continuous, then I will say that my function is a C1 functions. Now in case if I have a function say from Rn to R, okay, but Rn to R means I talked about the differentiability, right? Partial existence of partial derivative, I said direction derivative and total derivative. In that case, of course, similar sort of things will be there when I can talk about that function is in C1, but similar sort of definition will be there. But in that case, since the meaning of total derivative, partial derivatives are different from the real valued functions of real variable, so it is expected that it should be little different. And I think I'll start that one in my next lecture. Okay, thank you.